Yeah, thank you very much. So yes, as you heard, I was a student of Dénes, and this is why I'm going to give some overview of his results. And first of all, I would like to thank the organizers, Nilanjana, Andreas, and Josie, for creating this special session. I think that Dénes would be happy to know that he is commemorated at such a nice conference. Especially, he would be even more happy to see how many of his results are being mentioned in all sorts of talks and discussions. And I think actually one of the last conference that he attended and gave a talk was the first Beyond I.I.D. So it's also kind of special in this respect. Okay, let me start with a few more personal things about Dénes. Okay. So just 4 pictures very, very quickly. So the first one is from his high school student years. It's from a journal for high school students in Hungary. And when the question arises that some people claim that Hungary is quite remarkably successful in mathematics compared to its size. And one of the explanations some people attribute this to is the existence of this journal. So this was created about 100 years ago, I think by the teacher of John von Neumann actually. And this picture is, so the system is that every month they publish a set of problems, and the students can work for 1 month on these problems, and they can submit it. And in the end of the year there is an evaluation, and the best problem solvers get their pictures presented in the journal. So this is from that journal. And if you have any interest in it, you can find the picture of prominent Hungarian mathematicians like Erdős, Lovász, and many others. So if you want to see their pictures from their young ages, then you can find it there. Okay, the second picture shows him with 2 persons who were very important in his professional career and in life. Both. So he's Masanori Oya, you know, the quantum entropy and its use monograph. It was written together with him. And this is Fumio Hiei, who is also here in the audience, and he will give the next talk. This picture is just a random picture showing that Dénes was actually quite a cheerful person, despite of the impression you might get from the other pictures. And the last one is a slide of a talk that he gave in Wrocław in 2007. And it's a very, very appropriate picture because he's talking about John von Neumann and the entropy. And entropy was the focus of his research for most of his professional career. And John von Neumann was his mathematical idol. Okay, so I just wanted to mention these few things before I start the talk. And yeah, so the objective of the talk is to give some overview of Dénes's results, but of course the whole conference would not be enough for that. So as I wrote in my abstract, it's going to be a kind of subjective selection of topics that I like or find interesting, or I think that maybe not as well known as they should be. And necessarily I will try to give reference to a lot of other works, but I think unavoidably I will miss a few, so don't be offended if yours is one of them. But please let me know later. It would be very nice to see all the work that was influenced by Dénes's work and is related to his. Okay, and if you want to know more about his work, then here is a subtle suggestion from Matt Seinet, whom you should ask. So you can see that his work together with Fumio Hiei was very, very important, and he's also here in the audience. So you can turn to him for more information. And also, some of his co-authors are here, Anna Jancsova and Besra Sky. They are also going to give talks in this special session, and also Andreas Winter. So they know more about various topics of Dénes's work than me. And also Richard Joser, I think, is here. Yeah. So yeah, you can discuss also with them. Okay, so turning to his professional activities, I think Dénes was not, strictly speaking, a quantum information theorist or an information theorist. His background was in functional analysis and operator algebras. and quantum statistical mechanics. So if we accept the view that information theoretic problems have an operational and entropic sides, and coding theorems connect the two, then we may say that Dénes's work focused on the entropic side of information theory. There are some notable exceptions. One of them is Stein's lemma with Fumio Hiei, which concerns both sides of a problem. This is closely related to source compression, state compression, via the asymptotics of typical subspaces, and he also did some work on parameter estimation. And those of you who have ever read something from him might know that most of his work is in the general operator algebraic framework, but the techniques he's using lead to deep and non-trivial results even in the finite dimensional case, which is an interesting thing, I think. And in this talk I will be completely finite dimensional, but you won't have to wait for too long to satisfy your desire for more sophisticated mathematics, because the next two talks are going to be mainly in the von Neumann algebraic setting. Okay, so I think one of the questions that intrigued Dénes for a big part of his career is the basic problem of how to quantify the difference of two quantum states in a statistically meaningful way. And we know that in the classical case there are various measures which are very well established, like the Kalbeck-Leibler divergence. All of you know this formula very well. It's interesting to know that it can be written in this form with this function eta here. This will play a role in the future development. And another very prominent family of information measures are the Rényi divergences given by this formula, again very well known. And it's interesting that they can be written in the same form with a different function. And this was what Csizár noticed and independently Ali and Sylvie in the 60s, that actually many of the properties of these divergences can be derived from the sheer fact that they can be written in this form and some properties of this function f. Namely, if f is convex, then this divergence is going to be monotone and jointly convex. You all know what this means. And so a very valid question is what could be the quantum counterparts of these measures. And this is what this is the area where Dénes did, I think, his most influential work. So I will change the historical order a little bit. So no, sorry, that will be a bit better. Okay, so the question is how to generalize a classical divergence to quantum states, and I will show three different approaches that all come together in the quantum Stein's lemma. And the first of them is just to find some formula that resembles the classical one and show that it has some desirable mathematical properties. So an obvious minimal requirement is that it should reduce to classical for commuting states. It should have monotonicity under stochastic maps, joint convexity maybe. And historically one of the first one that was generalized to the quantum domain was Umegakis relative entropy. And a lot of people did some very remarkable work proving these desirable properties of the relative entropy. But there were other candidates also. For instance, the Belyavkin-Stashevsky entropy that we have heard before in Ludovico's talk, for instance. And now the question is whether we can somehow extend all these classical F divergences to the quantum domain. And here is where I will change the historical order a bit. So one possible choice would be, well, we obviously replace the sum with the trace, and this Q is going to be replaced by the second state sigma. But the question is how to divide two quantum states with each other. And one possible way would be to do this. I mean, if you want sigma commute, we get back the same formula. But it turns out that this is not very good because this is not monotone. So in this paper we have an example that even for quadratic functions this is not monotone. So this is not a very good idea. Another proposal was done by Dénes Petz and Beth-Raskai in '98. They proposed a formula which looks almost exactly the same as the above one, except that this division here is done in a slightly different way. And this seemingly innocent difference makes a huge difference actually, because it turns out to be both monotone and jointly convex. And in 2003, Matsumoto showed a very remarkable result, that this can actually be expressed by this optimization. Namely, we take all classical probability distributions that can be mapped to rho or sigma with the CPTP map. We evaluate the classical, sorry, this should be a DF here. So the classical F divergence of these two probability distributions. And if you take the infimum, we get exactly this formula. So it's very remarkable that such an optimization can have an exact closed form. But unfortunately, or not, I don't know, but there are no known operational interpretations of these divergences, although Ludovico has some idea how to get some operational interpretations, as we have heard. And it's worth mentioning that this Belyavkin-Stashevsky relative entropy is one particular member of this family, which we get corresponding to this canonical function. And it was Dénes Petz who was successful in extending this concept of F divergences to the quantum domain in a way that is useful. Motivated by the work of Araki, he introduced this formula, which is again an analog of the previous ones, except that we are not trying to divide the density operators themselves, but we take this left multiplication and right multiplication operator, which together give the so-called relative modular operator, which is a very central concept in operator algebras, and you will see them a lot, I guess, in the following two talks. And so this becomes a super operator acting on this operator. And if we define the quantum F divergence with this formula, then we get back the usual or the omega k relative entropy for this function. And we also get what we call these days the Petz type Rényi divergences, which are defined by this formula. And it turns out that with this choice, these quantum F divergences have the right properties. Namely, in an exact analogy with Chisar's theory, if F is not convex but operator convex, then it turns out that these divergences are monotone and jointly convex. And what is really nice about this is that, I mean, proving the same things for the relative entropy required quite involved techniques, and it was a long way to prove this result. And this general formalism allows for a proof that is basically a few lines only. So it's very elegant and very simple, and it not only extends but also simplifies the preceding proofs. And needless to say, everything works in von Neumann algebra, so it's true for most of the results I'm going to mention. Okay. So this result also was done in a successions of extensions and more and more precise statements. So the really important part was done by Petz, but there are various others who extended his results a little bit. And a key observation behind the application of these quantum F divergences is that every operator convex function can be decomposed in some more or less canonical form. There is a quadratic form at the beginning, which is not very interesting. And in the rest, we have an integral decomposition to operator monotone decreasing functions. So these are kind of primitives for the operator convex functions. And correspondingly, these F divergences can be decomposed as an integral of these primitive F divergences. And for instance, if we want to study the equality condition, so when this monotonicity holds with equality, then it turns out that it doesn't really matter which F divergence we study, as long as the support of this decomposition measure is large enough, it's the same condition for all quantum F divergences. So I'm just mentioning it now because I will switch between different F divergences sometimes. So it's good to keep in mind that it doesn't really matter which one we are using. Okay. And well, one of the best known and most applied results of Dénes is this characterization of equality. So it is trivial that if we can find a so-called reversion map that maps back the images of the states to the original, then we need to have equality because of monotonicity. And his big result was that it's also a necessary condition. So equality can only happen if this is satisfied. Moreover, there is a canonical reversion map, which is nowadays called the Petz reversion map, which can be given by this explicit formula. And it only depends on the stochastic map and the second state, and not on the first one. Okay, I guess many of you know these results very well, much better than me. So actually, I will be quite quick here, disproportionately to the importance of his results, and later I will mention some smaller ones in more detail because I think those are less known. Okay, so this result played a very important role in the constructive description of short Markov chains by Patrick Hayden, Richard Josa, Petz himself, and Andreas Winter. And we later generalized it for the structural description of triples where this monotonicity is satisfied with equality, and also Anna Jencsova and Dénes Petz further generalized these results. Okay, I should mention that in the past few years finding approximate versions of this monotonicity characterization was an extremely active field after the breakthrough results by Omar Fazi and Renato Renner. So I tried to list a few of the papers that I'm aware of. Please feel free to add the ones that I may not have listed here. I will mention a little bit more about these results later if I will have the time. Okay, but again, this is a topic that many of the members in the audience know much better than me, so it's better if I'm not spending too much of the time here explaining these results. Okay, maybe interesting observation which you also heard related to Ludovico's talk as a comment, that in fact another shortcoming of this other kind of F divergences is the preservation in this case does not imply reversibility, which was observed independently by Keiji Matsumoto and us. Yeah, this concept of F divergences is very fascinating. So it has been known that the standard Rényi divergences are a special F divergences, but recently these sandwich Rényi divergences have been introduced. I'm going to explain more about them later, which are known to be not to fall into this Petz type of F divergences, but Mark Wilder recently found some way to still rewrite them as F divergences. So maybe eventually everything will become an F divergence with the right definition of it. Okay, and since I'm mentioning sandwich divergences, I just advertised that sufficiency in terms of these new sandwich divergences, Rényi divergences, will be one of the central topic of Anna's talk. And related to this is a topic which is probably less known in quantum information theory. But in the past few days, multiple people asked about this one, so I would like to mention it very briefly. Namely that once we have these F divergences, it has been shown by Lesniewski and Besraska in 1999 that if we take the same state and we perturb it with some self-adjoint operator with a different perturbation parameter, and we take the second derivative at t equals x equals 0, then of course we get a bilinear expression which can be written in some sort of canonical form. So this mf hat rho written here is a kind of non-commutative multiplication by rho. It is given explicitly by this formula where again we have these left and right multiplication operators, and this f hat function can be explicitly given from the original f. And this is a non-commutative multiplication because if we have the proper normalization for f and rho and x commute, then this is indeed a multiplication, doesn't matter from which side. And this quadratic form turns out to be a very important concept mathematically because it has a sort of monotonicity property. So we can think the set of invertible states as a smooth manifold, and the tangent space at each point is the set of self-adjoint operators with zero trace. And we can think of this quadratic form as a Riemannian structure on this manifold. And it has the monotonicity property that if we apply a CPTP map, actually weaker positivity is enough on the base point and also on the operators of which we take the inner product of, then this monotonicity property is satisfied. And this is a very famous result of Dénes from 1904, who showed that first of all that these are monotone metrics, and vice versa every monotone metric can be written in this form with some operator monotone function. And this can be derived directly from his slightly more general concept of F divergences. Okay, And what I would like to mention is that once we have this non-commutative multiplication, we not only have this Riemannian structure, this monotone matrix, but also we can define a so-called monotone variance. So in the usual variance, you would have the same operator, so this is some kind of covariance, and you would have trace rho a square minus trace rho a on the square. But instead, you can choose any of these non-commutative multiplications, and you can define a corresponding monotone variance. And it turns out that they have a very similar monotonicity property to the one mentioned before, and actually these two ones are very easy to say to be equivalent to each other. So this is from a paper by Dénes from 2002, who has also shown that every monotone variance has to be of this form with some operator monotone function f. And he also derived some generalized Cramér-Rao bound. So if you have a parametric family of states parameterized by some parameter theta, which is some open subset of R, let's say, in the single parameter case, then we can define the so-called generalized Fisher information. So we just take the derivative of this density operator, which is a traceless self-adjoint operator. We put it into this monotone matrix, and we get a number. And this is called the generalized Fisher information, which actually coincides with the usual Fisher information, what physicists call Fisher information, for a particular family of states and a particular choice of this function f. And we have heard a lot about this in Iman's talk. And this generalized Cramér-Rao bound is of the form that the inverse of the Fisher information times the square of this derivative is a lower bound on this generalized variance. So this part becomes 1 if A is a so-called unbiased estimator. And this is a very pleasing formula, and it's very simple to derive. It's basically just Cauchy-Schwarz inequality. The problem is that it is not completely clear how to interpret this formula on the right-hand side. So the usual variance is statistically very clear what it means. These generalized variances are somewhat less clear. And I think this result is much less known in quantum information theory than most of Dénes's result. But curiously, if you look at Google Scholar, then this paper is his highest cited paper. So some people at least are very interested in this result. Okay, and let's get back to our original question. So how to extend a divergence to the quantum case? And another way to do that would be to try to recover it from the classical situation. So if you already know what our classical divergences are, what are the relevant divergences, try to do some kind of classical optimization. The motivation could be that if you consider a PVM, a projective measurement, which is actually a von Neumann measurement, so it's a rank 1 projective measurement, then it is well known that we can get back the von Neumann entropy by such an optimization from the post-measurement classical entropies. So maybe we could try to do the same for whatever kind of divergence that we are interested in. So we could take a divergence and define this von Neumann measure divergence. Here we take the supremum because the divergences have opposite monotonicity properties to the entropy, and we expect them to be monotone non-increasing under measurements. Or we can take more general projectively measured or POVM measured divergences. And the question may be if they give us some meaningful formula, something that is important in quantum information theory. And if they not, then we might go one step further and look at some asymptotic measured divergences. So we can take two sequences of states, which usually would be I.I.D. states. We normalize them because we expect the divergences to be extensive, and we see if we get something interesting in the limit. Okay, I will talk a little bit more about this later. And another process would be, which is dual to the one mentioned here, is the one proposed by Matsumoto, where instead of mapping the states into classical ones, we map classical ones into the states, but I have already discussed this one. So this leads to a mathematically very nice divergence, but it's less relevant in quantum information theory. Okay, and the final and decisive way to extend a divergence is to give it an operational interpretation. So, I mean, the divergence is ultimately a good measure of information if it appears naturally in some operational problem. And this is exactly what I.I.D. and Petz did in 1991. So this is their very famous quantum Steins lemma, or often also called I.I.D. Petz theorem. So I'm sure that most of you are very familiar with this, but let's just very briefly summarize what it says. So we have two states, rho 1 and sigma 1. We have many copies of a quantum system prepared in either of these two states. We don't know which one, and we want to make a binary projective measurement to find out which the true state is. Obviously, there are two ways to make an error, which give the type 1 and type 2 errors expressed by these two formulas of confusing one state with the other. And the setting, which is very common in statistics, is to keep the type 1 error below some threshold epsilon and optimize the type 2 error under this constraint. And the content of this quantum Steins lemma is that in the asymptotics, if you go to many copies, then under this constraint, this quantity decays exponentially fast, and the exponent is at least as good as the relative entropy, the omega k relative entropy of these two states. And there was also a converse version which says that we cannot do much better than this. Namely, for a fixed epsilon, there is a lower bound like this, which becomes exactly matching in the limit epsilon goes to 0. So this is the so-called weak converse to Steins lemma. Okay, and this gives the operation and interpretation of omega k's relative entropy, and this was the decisive argument to use omega k's relative entropy in quantum information theory and not other relative entropies, at least for the purposes for which the Kalbeck-Leiber divergence is used in classical information theory. Okay. And what I should mention is that actually the original paper is not in the setting that I have just explained, because it is non-I.I.D. So the second state was a product state, but everything that I explained holds also if instead of the tensor powers we take rho n and sigma n, where sigma n is still a tensor power, but rho n is an n-side restriction of a so-called completely ergodic state on an infinite spin chain. So we had some tutorial about ergodicity on the first day. It doesn't really matter right now what complete ergodicity means exactly. And this was actually extended to even more non-I.I.D. scenario, where the first state was kept ergodic, completely ergodic, and the second one was a so-called strongly mixing finitely correlated state, which I'm also not going to explain what it means. I would just like to point out that this was beyond I.I.D. in quantum information theory, well beyond, or well before quantum information theory as we know it today was actually born. So if you look at the dates, then this is before Schumacher compression or Holevo-Schumacher-Westmoreland theorem or any of the big results that we know in quantum information theory. And this is not very surprising, because also in the very beginning of information theory, people have recognized that the coding theorems don't really depend on the I.I.D. condition. It depends on that certain quantities converge somewhere in the asymptotics, and these are laws of large numbers, and they hold under various correlated scenarios. So it is very natural to consider quantum information theory and quantum information theory in the non-I.I.D. scenario. And usually we get nice expressions in the asymptotics if we know at least something about the correlations of the state that we are working with. Okay, so actually this result was strengthened by Ogawa and Nagaoka by showing the so-called strong converse, that namely that this limit is actually true for every epsilon between 0 and 1. And the result was made even more non-I.I.D. with a succession of works by Bielakovic and co-authors, who has shown analogous Steins lemma results when rho is ergodic and sigma is I.I.D., or even more generally when rho is translation invariant and sigma is so-called star mixing, which is basically just extracting the relevant property from this set of states. Although their error criterion is a little bit different from this, so it's not, but anyway, it's irrelevant now. Okay, yeah, so generalizing quantum Steins lemma for other scenarios has been an important research line in quantum information theory. First picked up maybe by Hayashi in 2002, who has given a composite version of Steins lemma, where the null hypothesis can consist of several states, and he was using group representation theory to get such a Steins lemma. and later by Bjelakovic et al. And I also have some method to prove such a result. But the converse version, when the alternative hypothesis is composite, turned out to be much more difficult. And there was a very nice result by Brandau and Plenio in 2010, which is not exactly the straightforward I.I.D. generalization of or version of the Steins-lemma with composite alternative hypothesis, which kept to be an open problem for a long time, until very recently in a very nice paper, Mario, Berta, Fernando, Brandau and Christoph Hirhe managed to solve it. So Mario and Christoph are here, and I think you could see the result in the poster. So if you haven't yet done so, then do it, because it's very nice. Okay, what else do I want to say about Steins-lemma? Indeed, that it's an almost trivial but very important observation, is that if you replace this reference state, by the identity, yeah. So I should have written so this is just the identity, this sigma n. Then Steins-lemma is still working fine, and what we get here is that it says that there exists a projection for every epsilon such that most of the weight of this state is concentrated on the subspace in the range of this projection, whereas the dimension of this subspace is growing with the entropy. Yeah, it's here, sorry. Okay. So this was already observed by I.I.D. and Petz in a series of works in 1990, and by I.I.D. and Petz in 1994 in this very non-I.I.D. scenario. And this is basically the key part of the achievability part of source compression behind that was given by Schumacher and Josa in 1994. And what is nice about it is that it works for correlated sources also. So source compression can be formulated in many different ways, but one way to formulate it is that you have a state and you want to preserve correlation in a purification, and you want to compress it to a lower dimensional subspace. And what is interesting in this correlated state case is that the successive density matrices don't commute with each other. So it's, even though we remove a lot of non-commutativity by only considering one single state in Steins-lemma, and the other state is the identity here, but still there is a non-commutativity of the successive density operators. So it's a highly non-trivial result. Okay, and I wanted to say a little bit about the proof method. I hope I will have some time for that. So the method, which since has been used in many other scenarios, is to reduce the problem to a classical one by making a suitable projective measurement on a large enough block. And then we get some classical states with some classical relative entropy, and we have to show that the measured relative entropy converges to the true quantum relative entropy when the block size is increasing. And the converse can be shown using the monotonicity of the relative entropy or the monotonicity of the Rényi relative entropies. So as you can see, all the ingredients that we have discussed, we have been discussing so far, monotonicity and measured divergences, make an appearance in this proof. Okay, and I would like to mention that many of the extensions of Steins-lemma use the same approach, and also our strong converse exponent proof and Hayashi's is following the same. And it's interesting to note, for those who are familiar with it, that this method is not the right one sometimes. So showing that the direct exponent coincides with the test type Rényi divergences, which was done by Hayashi, Nagaoka, based on the work by Konrad Udenart and others, and Nussbaum and Shkoa. In that case, this method doesn't work. Okay, so I would like to mention very briefly a few of Dénes's observations and results related to this problem. So we go back to the question of recovering quantum divergences from classical ones via post-measurement divergences. So one of his early results was to show that if you make a projective measurement, then you can have equality of the post-measurement relative entropy with the quantum one only if the states commute with each other. If you look at the proof, it's pretty complicated. It's also in their monograph with Oya. But sometime later he gave up with an extremely simple proof, which I would like to see because it's so simple and beautiful. So it works for any POVM, and it uses the 1/2 divergences instead of the relative entropy. And one can just observe that this divergence is given by this formula. This is a trivial identity, so we just use that these operators sum to 1. And here you can use the simply a Schwarz inequality for the Hilbert-Schmidt inner product. You get this expression, which is exactly gives you the classical d1/2. Okay, so that's all the proof for the monotonicity. And the good thing about it is that because it relies on Schwarz inequality, we know the exact condition for equality. So in Schwarz inequality, you have equality if and only if one operator is a constant multiple of the other. Because of the traces, this has to be non-negative. You can multiply by mx1/2. You can sum over x. And then you can multiply from the right by sigma minus 1/2. Then you will get the superprojection of sigma here. And you can multiply from the left by the superprojection of sigma again. So what you get here is self-adjoint. So if you take the adjoint, then on the left-hand side, the order of the operator switches. And if the support of rho is not larger than the support of sigma, then this gives you exactly that rho 1/2 has to commute with sigma 1/2, and so rho has to commute with sigma. So this is all the proof. It's beautiful, I think. And it's been used very often in various scenarios. Okay, and because of the arguments that I mentioned before, it doesn't really matter which F divergence we take. It will work for any F divergence when F has a large enough support. Okay, so it shows that we cannot achieve the quantum relative entropy by one single measurement. What if we optimize over measurements? Is it still true that it implies commutativity? And I remember that Marco Tomamichel and David Sutter and some others were discussing this problem in a previous edition of Beyond I.I.D. in Banff, because apparently somehow Dénes either considered this trivial, and actually in some of his papers it appears so for the projectively measured relative entropy, but somehow it seems it has never been written anywhere explicitly. So for general F divergences, we wrote it in a paper with Fumio Hiei, which is actually an extremely simple argument, so maybe this is why Dénes didn't bother to write it down. So we know that this divergence is jointly convex, so it's enough to consider extremal POVMs, and it is well known that extremal POVMs don't have more than lineage square outcomes. So we get a compact set, and then we can use some sort of continuity argument to see that this supremum in the definition of this expression is attained. But it's not entirely trivial, because these quantities are not continuous in general, they are lower semi-continuous. But that would only give us that they achieve the minimum on a compact set, and we want to achieve a supremum. So one has to be a little bit more careful, but still it's pretty easy to finish this proof. So one gets that indeed for basically any quantum F divergence, if the measured version coincides with the quantum version, then the states have to commute. And Mario Berta, Omar Fazzi, and Marco Tomamichel have a different argument, which uses a variational formula by Petz, which I would also like to mention if I will have the time. And they also have it for the sandwich-Rényi divergences, which is a stronger statement than for these F divergence type Rényi divergences. Okay, just a few words about these measured divergences. So it is interesting to know that this measured divergence, no matter what kind of divergence we define it from, is monotone under positive trace preserving map, irrespective of the monotonicity properties of this delta. So one may ask, so this is in some sense a nice quantum divergence. When is the projectively measured one going to be a nice quantum divergence? At least monotone under CPTP maps. And it turns out that it is a very restrictive condition. And for any convex function, this projectively measured F divergence is monotone under CPTP maps, if and only if it satisfies a much weaker, very natural condition that it is invariant under isometries, and which only happens if it coincides with the measured relative entropy or measured F divergence. Okay? And in a very nice paper that I already mentioned, Mario, Omar, and Marco showed that for the omega p relative entropy and for the, well, actually it doesn't matter which relative entropy, and for the Rényi divergences, these quantities indeed coincide. And as I mentioned, it's based on a variation of formula by Petz. And Fumio here, he has some extension of this for a larger class of functions in some unpublished notes. Okay, and I'm running out of time. I have 5 minutes, and I have enough material for another 2 hours, I think. So I will very quickly flip through the slides and just try to highlight a few important parts of it. So we have seen that we cannot achieve the quantum divergence by these measured versions, no matter how we measure them. So the next one is to try to achieve them in the asymptotics. And this is the key point in the quantum Stein's lemma. So this was observed by I.I.D and Petz, that if you're using the relative entropy and you look at many copies, then you can use something which is called the conditional expectation property of the relative entropy, and this will give you two-sided bounds between the quantum relative entropy and the projectively measured one. And this tells you that in the asymptotics you can recover the quantum relative entropy. Okay, and from this they could show that the omega k relative entropy is less than the Bayevkin-Stashevsky relative entropy, which is given by this formula, which is larger. So this is larger than the projectively measured. And very interestingly, there is a lower one which looks almost exactly like the Bayevkin-Stashevsky, just that again inside somehow the division is done in a different way, which I think is very pleasing. Okay, and what I would like to mention is another result by Dénes. So actually this conditional expectation property in this particular case can be verified very easily. Of course he proved it in the von Neumann algebraic setting based on or continuing this paper. But what is very interesting is that if you assume a few very natural properties and monotonicity and the conditional expectation property, then these determine uniquely the omega k relative entropy. So there is a kind of axiomatic way to obtain the omega k relative entropy, which also excludes, for instance, the Bayevkin-Stashevsky one. Okay, so this kind of argument was generalized and put to a higher level by Hayashi, who observed this pinching inequality, and he used it to get a host of very impressive and nice results. But I'm not going to explain that in detail. I only mentioned that this can be applied also to the sandwich Rényi divergences, which was introduced in these two papers. And this observation is the main reason why one can determine the strong converse exponent and get these sandwich Rényi divergences. I would only like to mention that here in the asymptotics for the measured and the projectively measured, in the I.I.D case we can recover the sandwiched Rényi divergences, but only for this parameter range. And for alpha smaller than 1/2, we get this slightly strange expression where the two states are swapped and the alphas are a little bit messed up. And the reason is that again in this paper it was shown that for alpha smaller than 1/2 these divergences are anti-monotone under projective measurements, but one can use this symmetry property for the measured relative entropies, and one gets this split expression, which I don't know how widely it is known. Okay, here I just wanted to mention some very general mechanism to get similar results, with which one can extend to even more non-I.I.D situations very easily. It's a beautiful trick actually based on a paper or actually hidden in a proof in a paper by Marco and Masahito. So if anyone is interested, I would be very happy to make more publicity to this result, because I think this is beautiful. And I would close my talk with mentioning this variation expression of Dénes, which featured in many recent works. So it's based on a technique by Araki. So if one has a state or a functional and a self-adjoint operator, then one can define this perturbed functional. And a trivial observation is that this is a state, so this relative entropy is non-negative. We can get an explicit expression for it. Equality holds if and only if the two states coincide. And if you choose these A and B, if you are given two self-adjoint operator A and B, and we choose H and sigma and rho in the right way, then we can get a two-line proof for the Golden-Thomson inequality. So this is really just the proof. And the nice thing is that this is based on the monotonicity of the relative entropy under measurements, projective measurements. And because Dénes has characterized the equality case for this, and I have shown you that this is another two-liner, one can see that equality holds here if and only if the two states commute. So again, in a few lines we can get Gordon-Thomson with a characterization of the equality condition. So this is one very nice application of this variational principle. The other is that if we rearrange it for this quantity, then we get a variation expression for this generalized free energy. And if we take two states and define sigma and h in the right way, then we get a variation expression for this kind of Rényi divergences, which played a very important role in the strong converse proof for classical quantum channel coding. And they are also a special case of this family of alpha Z divergences introduced by Niranjan and Konrad Udenart. Okay, and finally I just mentioned that Dénes and Fumio Hiei also gave so from this you can get a variation expression for the relative entropy, and with a very simple argument you can get a variation expression for the projectively measured relative entropy. And this featured in this paper that I mentioned already several times, and they also gave a different proof for this expression and some variances. And this is the last thing, the last thing I mentioned in my talk, is that in another paper, in this paper they have shown a four-matrix extension of the Gordon-Thomson inequality, and using these two variation expressions, they could give again a few line proof for this this monotonicity lower bound in terms of rotated Petz recovery map, which is for the partial trace, but with standard techniques it can be generalized to arbitrary CPTT maps. So yeah, the only other thing I would have mentioned is this divergence ready representation of the classical Holevo capacity of a quantum channel, but I'm not going to talk about that, and I'm closing my talk with this. Thank you very much for your attention. And thanks a lot to the organizers again for putting up this special session.
Thanks for doing this. Okay, any questions please? Remarks?
Well, I'm sorry it was a little bit rushed, but you see there are so many results of Dénes that it's hard to fit it into a 40-minute talk. Yeah, if you have any historical remarks later or whatever results you know is connected to Dénes' work, then I would be very happy to hear about it later.
Okay. In that case, let's move on to present.